Mostly Iceland projects.
Thank you.
So up to now we heard about lukewarm geothermal, now comes the real stuff. So that picture that you see is the Krafla geothermal field in northern Iceland. And that's operated at temperatures somewhere between 250 and 300 degrees C, so that's quite nice already. And this technology has been operating, this has been around for quite a while. This is another one. This is in southwestern Iceland. That's the Hellisheiði power plant. This is, in principle, the one with the biggest capacity in Iceland, up to 300 megawatts. They could, in principle, run if they wouldn't deplete their field too quickly. And it has a quite noticeable feature as well. You see this pipe down here. That's actually for re-injecting the stuff they took out, plus CO2, and this is wrong, this is not SO2, it's H2S, to sequester it in the underground. So there's quite some intelligent stuff ongoing as well. Now, as I said, that has been around and is worldwide, and we heard this before, it's exclusive to volcanic areas. So you need magma to make these very hot fluids, and we learned already that this is where that is, in the sense, not matching supply and demand. But I think I want to raise a few points about this. There is areas where this is actually very interesting in terms of changing to a greener world. As you will later hear, I guess, from Luis, the change in terms of electric cars and whatever requires a hell of a lot more copper than we currently have, and all this copper, or almost all, comes from Chile. Now, these copper mines are somewhere in the Atacama Desert, and there's nothing to supply energy, but they have in the Andes, actually, hydrothermal systems, and this is one of the ways they explore now, how they could get actually electricity for the mines that they have there. Then also Eastern Africa is currently booming in terms of developing these kinds of resources, and we heard yesterday in particular that you have a developing country transitioning to a higher economic state, and Eastern Africa might be one of those where these things could be of relevance. Anyhow, so what is typical to these? Groundwater is heated to more than 250 degrees by magma bodies that sit at some kilometers depth. It's a rather mature technology. The Italians started this more than 100 years ago in Ladorello. We'll hear more about this tomorrow. And they're still operating that at a few hundred megawatts, so electricity, so that's not too bad. And the typical reservoir temperatures are 250 to 300 degrees C. Developing and operating a field is basically considered an engineering exercise. So when you go to one of these places, you barely see a geologist or geoscientist, and there's surprisingly little geoscience input. I came into this field maybe 10, 15 years ago, and I was surprised when you talk to the people there what their conceptual understanding, in quotation marks, was. So my main sort of science interest is actually ore deposits, hydrothermal ore deposits, and we are all used to doing this kind of exercise. You have a source for your metals, then some fluid that picks them up and deposits them in a concentrated form somewhere else. And obviously, if you apply this view to one of these systems, it's sort of the same thing. You have a strong energy source, which is the magma. Then you have some groundwater that's getting heated by it, gets into a convecting mode, picks up the heat, and then up here is what your reservoir is, what you target to exploit. So that's pretty simple, but actually what practitioners look at it, in particular engineers, is this. So they have some hot stuff here, you can drill into it, produce it, but you have no clue what the boundary conditions are. And even more so, the tools they develop to model and understand this, they totally ignore the heat source. So what you do for a reservoir model is you modify this boundary condition until you sort of match history, and then you basically have an infinite heat source down there, and then all your decisions are based on that. So over the last 10 or so years, this view has changed a bit, and Sebastian and I, when he was still, or just after when he finished his PhD with us, were playing around with work that Dan Haber and Steve Ingebrigtsen from the USGS did in terms of modeling, and tried to understand the systematics of these systems a bit more. So this is a snapshot from a very simple-minded simulation. You have a hot body down here, then you have some permeable medium surrounding it. This is 4 kilometers down, 10 kilometers in here. And basically there's all relevant physics in there. So all water properties as a function of temperature and pressure, including boiling, There is the decay of permeability with temperature, because then the rock becomes ductile, closes pores and fractures, etc. And so the only remaining thing that you actually have is modifying the permeability of the rock surrounding it. And if you do this exercise, then actually if you go to 10 millidarcy homogeneous permeability, uniform permeability of the host rock, you get this picture. So these plots are very common. This is 0 to 2 kilometers depth along this profile here on top of the magma body. This is temperature from 0 to 400 degrees C, and the different lines are actually different stages in the evolution of the system. So it's temperature with depth that these lines record. When this thing intrudes, it starts to heat it up, so the hot water flows up, but it loses heat to the then still cold rock, right? So you're building up a plume that rises, and so in the early stages you have temperature profiles like this. On top, the water still follows the geothermal gradient. Then you hit the plume, and down near the magma, it's already heated. And after a while, it has heated all the rock on top of it. And if you have this permeability in the host rock, you get actually a system where you have isothermal upflow at about 250 degrees C, and then boiling over the uppermost 400 or 500 meters. And this actually reflects several things that will come up sooner. But the other thing is, after a while, your heat source is depleted, right? And then you get the cool groundwater hitting something that is still maybe a bit warm. And you have this rock mass that was heated by the fluid before. So what will happen now? The stuff will cool from below. So after some time, you get these things where the temperature goes down and the upper part is still boiling. So you can't even distinguish, is your system dying or is it still in its main stage? Okay, now what is very different from other groundwater flow applications, etc., is now if we change the permeability comparatively little to 0.1 millidarcy, the thermal structure is a totally different thing. Now, this is basically a conductive thermal profile, hardly any convection, and so this system is not very efficient. And in between these two is the hottest system type. You get in the main stage, when the system has fully heated up, boiling to 2 kilometers depth, 350 degrees, and when it cools down from below, you get these inverse thermal gradients here, and then boiling still at the top. So over a very small range of permeabilities, the system behavior is totally different. And so many people, many practitioners didn't even know this basic thing. What happens there is basically, in a nutshell, inside this hot body, heat can only be transferred by conduction, and outside it's by convection. So you have two different heat transfer mechanisms there in competition. If you have a lot of permeability here, you can move a lot of water around that, but the heat supply is limited, so you get only relatively cold water. This case, if you had 10 to the minus 13, you would reach only 1 E minus 13. You would only reach 200 or 180 degrees. If you had relatively low permeability, the fluid is so slow that it picks up a lot of heat, but on its way up it loses all that, so it doesn't even disturb the local geotherm. And in between you have the optimal thing. You basically pick up a lot of heat, and on the way up you don't lose it anymore. So, or you lose only relatively little. So if you understood this, you can understand these systems. As geologists, we then tend to, when we look at the real system, there's faults, there's fluid-rock interaction, there's blah, 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 and all the complications, and we don't see the forest from the trees. But if you have this as a reference point, you can understand these systems. Anyhow, if you plot this onto a diagram that geothermalists know a lot, this is actually specific enthalpy, this is pressure here on a logarithmic scale. Then actually the boiling curve opens up to a field because you have enthalpy, you have a high enthalpy vapor phase, a low enthalpy liquid phase. And if here is somewhere the critical point where water can't decide anymore whether it wants to be a liquid or a vapor. So if you plot these three things here, at this permeability, basically you start up down here. This is about the depth where the magma is. You don't heat it to more than 250 degrees. And if you let it flow adiabatically up, you see the isotherms and the adiabats are basically parallel, so that's why it has this isothermal upflow. Then it hits the boiling curve somewhere here, and in the upper part it has to follow this temperature pressure curve because boiling temperature is a function of hydrostatic pressure here. If we have the middle one, we can heat it much, Because it's flowing slower, it will actually lose a bit of energy, but basically it hits the boiling zone pretty early on, pretty deep, and this will give this system. And this one gets very hot, but it loses all the energy when it rises. So this is the first order picture. This image, we learned later, is not quite correct, but the essence is good to convey this way, and so we leave it like this. Anyhow, a few examples. Well, then the Icelanders were pretty smart. In Italy, in New Zealand, wherever you have this, people drill 1 to 3 kilometers. And we don't know why they don't drill deeper, but it can be because the boiling curve with depth, it steepens the deeper you go, so the temperature doesn't increase anymore, so it's probably not very attractive going deeper because you don't gain more energy. Well, on the other hand, this is 200 to 300 degrees, and the magma that heats it, it's like 800 to 1200 degrees. So anywhere in between must be something that's hotter than 200 to 300. And that's when the Icelanders came up with the idea of doing their Iceland deep drilling project. And it would be actually pretty advantageous to have something like this. Conventional resources are somewhere here. And when you rise, you actually produce more and more liquid and a bit of steam. It's all relatively complicated in terms of handling. If you had a supercritical or a super hot resource somewhere here in the diagram, 500 degrees, 300 bars, and you would actually bring it to surface, you don't intersect this, so you have dry steam that comes up at very high enthalpy, and this would be very attractive. So that was the idea behind it, and Iceland, in around 2000, formed a consortium, the Iceland Deep Drilling Project, and former Statoil, now Equinor, and several others involved as well. And so this was the first one they did. So this is the first well, IDDP-1. It's in Krafla, that was on the title slide. Basically, this is the drill rig in 2009. There's a few geologic features here. On this plateau here, you see a few dark features. That's dikes and lava flows from the Krafla fires that were on in the 1970s, early 80s. So active volcanic eruptions in a geothermal field. And this is the Viti crater. That's from the Mývatn fires 300 years ago. This is a hydrothermal explosion crater, and you had active volcanism 300 years ago. Now all the anecdotes about the system, you had geophysicists coming in, doing MT, saying, this is the place to go, no magma there. Well, I mean, I don't know. And so what they did, actually, they drilled. They expected to go 5 kilometers, find 500 degrees, 300 bars. So at 2 kilometers, the well got stuck. They couldn't do anything, cut it, deviate it. At 2 kilometers, got stuck on the second attempt, third attempt, same thing. They looked at the cuttings, oh, glass. And so they drilled into magma, rhyolitic magma, and then they actually closed the valve and let the well stay there for a while, decided what to do. And then after a year or so, they ran flow tests, and it's really impressive. So at the wellhead, 450 degrees C, 140 bar. Very different thing, 200 degrees hotter than the rest in the field. And from the flow test, they estimated from the single well, if they could operate it, they could get 35 megawatts electric energy, which is about 8 to 10 times more than the average geothermal field well in these fields. So if you can do this, this will be a real game changer in these things. And that's why there is quite some interest in exploring this. Obviously, there are technical difficulties. Nobody has ever done such thing. And so there's a lot of engineering exercises ongoing now to get a hold on that, but nevertheless was interesting. 2 videos just to give an idea. This is now a video just a few minutes after they opened the well. And so I switched off the sound here because it's really jet engine starting, and you see very dark steam coming out. This is actually due to mechanical corrosion of the casing. So not very nice stuff. And then after about 20 minutes, half an hour, it's actually clear superheated steam. That's the 450 degrees stuff coming out and then getting chilled in the Icelandic coldness. And yeah, that's the stuff. Now then 2 years ago, they drilled the second one. That's now on the southeastern end. That's where the mid-Atlantic ridge comes onto land. They did it in the Reykjanes field. There's actually seawater, the circulating geothermal fluid, and they used an existing well deepened into 4.6 kilometers. So 2 days after or 5 days after they drilled it, they ran a temperature pressure log, and they found at the bottom 427 degrees, 345 bars, but this was when the well was still heating up after it had seen all the cool fluid. Then there is no newer data because basically the casing at 3-point-something kilometers started to buckle, and so they can't send anything through anymore, so they don't know what's actual temperature down there. And so, yeah, this is the big question now. We're working with Equinor and others to get a rough idea of what could be there, and that's what I will introduce over the next few slides, and a bit of learnings that we had, because I see I'm running out of time. I skipped this slide, almost skipped this slide, just about supercritical. As somebody said yesterday, Martin Blunt was it, I think there's nothing critical in terms of risk or so. It's just a fluid at high temperatures and pressures that has some properties that are different from what you have below. Up to 374, 220, 374 degrees C, 220 bar, you can boil a liquid or condense a vapor. Above that, you have a gradual transition from liquid to vapor, and this has some advantages for handling the thing if you want to do power. Sam Scott was a PhD student of mine, and then using our own simulation platform simulated what geology controls the formation of these resources, and there's a lot in this slide. Basically, this is the simulation domain, 4 kilometers deep and some kilometers wide. We stick an elliptic intrusion and see what happens to the fluid here. And basically, if you have a permeable host rock, we see the same effect as before. You have a lot of fluid passing by, the resource is small. If you have it less permeable, you make a big resource, but the flow rates are lower. So, yeah. Then if you do this with something that has the properties of this Krapler field, actually this is where they encountered the conditions, and the simulation automatically gives this without tweaking any knobs. It just does that. Physics does that. And so we think with this approach, we got roughly the physics right. And it's important to get it close, to drill close to the magma. So it will be challenging if you want to exploit these. Another learning is actually, then in the computer you can add traces and things like that, at least if your code allows you to do this. Again, here's the intrusion. What we then did is whenever a package of fluid entered the supercritical zone, we gave it a tracer. 100% of this tracer, I'm supercritical, and then followed how the tracer is dispersed through the system. And if you do it like this, you can understand these conventional high enthalpy systems basically as just supercritical fluid being diluted from convecting lower temperature groundwater. And all of a sudden, some enigmas that we had before of because there was this paradigm, geothermal systems are adiabatic flow. And obviously, this is not the case at all if you have mixing with cooler groundwater. So this resolved a lot of uncertainties and enigmas about this thing. Another one, if you stick chemistry into that, in this Krapler field, you have one type of wells where you get very acid fluid and your well is done in a few days because it corrodes like hell, and then you have the normal geothermal ones. And there were all sorts of complicated models why this is the case. Turns out, basically, depending on what flow path you have in such a system, you get this. And the reason is this supercritical fluid is a chemically very friendly thing at this condition, because water is a low dielectric medium. At those conditions, all ions stick together. HCl is non-corrosive at all because it's a neutral molecule. Only if you put it into liquid water at lower temperature, it dissociates and makes all the stuff. And depending on where the supercritical fluid goes here, actually, it gets acid or not. So very simple explanation to that. IDDP2, I said it's seawater. It gets more complicated. This is the phase diagram of water. You have the boiling curve. Then I spent quite some years to derive this thing with all the quantification of fluid properties. This is the phase diagram of salt water, and this black tunnel is the one where you can have liquid plus vapor coexistence to very high temperatures and pressures, so very different. If you imagine brachianess, actually the question is, where does the fluid circulate through this phase diagram? And this will affect what you can do with your fluid down there, whether it's liquid plus vapor, liquid plus salt, or vapor plus salt, and so on and so on. And the key thing that you should see here is this red curve that runs on top of the black tunnel separates the side, this back side, which is the liquid side, high saline, high density, the front side, vapor, low density, low salinity. And you see it's the composition, which is this axis, is a function of temperature. So if you hit the surface at low temperatures, your fluid is liquid-like and will start to boil. If you hit it on that side, actually, it will be a vapor-like density at the same salinity, but it will condense out some liquid that's saline. And this actually in the simulations, well, I skipped this just as a question of time. So this is the phase diagram now flipped upside down. Depth, temperature increasing to the back, salinity here. And if you have now an intrusion at 5 kilometer depth and you get some convection cell, then your fluid will circulate down here and hit the blue surface, the liquid side, and then condense out at, wrong, the vapor side here, the red one, because the critical curve goes to higher salinities, and it will condense out a bit of liquid, but it will stay a vapor-like low salinity fluid, which rises rapidly because it's buoyant. If you have the intrusion at shallow depth, actually you hit the thing on the liquid side, and you basically stay liquid and you boil off a little bit of vapor. And this, if you run the simulations, basically, I go the slide back. What happens here, the intrusion is at 2.5 kilometer depths, here at 5 kilometer or 4.5 kilometer. Basically, and now, this is now at above the shallow intrusion, you make a layer of salt and dense brine. Very unattractive because low enthalpy, low mobility, bad heat transfer. If you have a deep intrusion, 4.5 kilometers, you make a lot of vapor, it's very buoyant, very high enthalpy. And so this is actually what we think the Reykjanes system is. They by chance got into this, and this is what we predict. We're currently working with Equinor and others to see what they can expect at this failed borehole. So some take-home messages about, I explained this, but this was the question of the meeting. So what about geoscience input to it? And I think in these systems, it's high value because we can provide a conceptual understanding of these systems, which engineers often cannot. And I think this is crucial for planning and decision making. It doesn't work if you do your business, your usual business as usual reservoir modeling with your standard tools, because they simply can't handle these conditions. And don't use them as the proxy because the thing is very different. That's standard. And what I also like to actually highlight is fundamental science is key to success for that. If you haven't done the science, you don't understand this. And in other things, what I don't like about top-down designed research and development roadmaps is often like, yeah, we take the tools we have now and then we develop some new technology. And if this doesn't apply, how shall you do that? I mean, it's lots more here, but I stop now. Thanks.
Thank you, Tom. To make a link to your talk, I mean, you're starting to talk also about the skills needed for the transition, which is very much what we're moving on to. So I like your concluding slide. I'll also say, since I was involved in the project, you know, to get that deep drilling, we need to bring in oil industry technology to get them down there. They couldn't have got down to those temperatures without some new technology. And we actually cool that borehole to 200 degrees cooling to achieve that target. So it's quite groundbreaking drilling, actually. Okay, questions from the floor? Yeah, in the middle here.
Yeah, just about the casing. Why is it necessary, you think, to put the casing down there? Are they not granite and they're intact, these wells?
I'm not an expert on this, but I mean, you have this like 4.6 kilometers, and then you start to heat it up by hundreds of degrees. I mean, this makes a thermal expansion that is gigantic. And if this hadn't been accounted for, then you get some buckling, I guess.
And then after that blowout, you said the casing just...
No, there wasn't any blowout.
No, but the black steam coming off, you said.
Oh, no, this is the different one. That's a different one. Yeah.
We have a well engineer in the room.
Hello, it's me again from the BGS. I'm on the planning committee for the next well at Krafla, and one of the things we're looking at is the casing problem. When you're drilling at Krafla, when you get down to about 1,800 metres, you've passed through the 450 zone where the water is, but then you have a massive loss zone, you get no returns. So we have to case that off before we can drop into the magma to core the magma. So the pH down there is about 2 or something. So
the pH is 2 when you bring it up and cool it. It's not in situ.
But the metallurgy just can't handle that. It'll just turn to tin foil in days. So one of the things we're looking at is thinking of cementing it and then drilling through the cement So we end up with cement, but then we've got all the thermal and conductivity problems with cement, because the last thing we want to do is to be able to bring thermal energy back up the well, because that's what leads to the buckling of the casing, because you have to anchor your casing at the bottom, then anchor it with a casing hanger, and when it starts to expand from the heat, it can't do anything, it just buckles, because the burst strain is so high, it can only buckle.
Thank you, John. Other question there? And behind as well.
I'm sorry, I'm going to be controversial.
Go ahead.
I've seen so number of these projects which absorbs huge sums of funds and resource. And actually, we should be addressing what Charlotte was saying, something directly applicable to climate change. There's a program, similar one in Japan, which I'm aware of, going around in circle. And I think what Charlotte was saying was absolutely right. This is where we need to address to change the climate.
Good. I'm sure the Icelanders wouldn't agree with you, but I think you're probably right. So, Lee? Go ahead.
I am Adele Manzella from Italian National Research Council, and I will talk tomorrow about the twin project in Italy. I will try to, I cannot go into the same detail, but I will try to explain tomorrow. It's not a matter of smartness in relation to Italian projects or experience, and it is not a matter of roadmap, because all this has been very well phased in the roadmap and in the strategic research agenda that I will talk about tomorrow. Just to testify that there is some smartness, just a comment. You mentioned at the beginning the need of geothermal also in relation to mining. Enel Green Power built a power plant in Chile, the first power plant in Chile, exactly to power a copper mine. I don't know, I'm not sure about if it is copper or what, but it is a very large mine in the Atacama Desert. And it is exactly because the plant is very far from grid, but can provide power to the mining. So tomorrow I will go in more detail about roadmaps and how these kind of projects can relate to climate change, because going deeper and exploiting a different kind of supercritical resources can be done in principle everywhere if we discover better, not only in this kind of environment, which is very permeable, essentially, but also in other conditions, also in deep crustal condition.
Thank you, Adela. So your hot geothermal also created a hot debate.
That's true.
So
That was the idea why
I very much appreciate
I
it.
presented it.
But thanks again to Thomas for a great talk.